Okay. Thank you very much for this introduction. Um, I'm representing a group led by Piotr Cisło. We are based in Toruń, which is not so far away from Warsaw. It's famous for being the birthplace of Copernicus. It's a really nice small town, an order of magnitude smaller than Warsaw. So today I'll speak about our results, the results that we've obtained in a joint theoretical and experimental study of cold molecular hydrogen. So you see that I'm switching gears to a much simpler molecule, and I think it's beautiful, especially from the theoretical perspective, because it only has 2 electrons, and world-leading specialists in hydrogen theory actually can predict the energies of vibrational levels within the ground electronic state of H2 with 10 digits precision. On the experimental side, it's also a very appealing molecule because its symmetry suppresses spontaneous emission, which makes all these vibrational levels exceptionally stable. We are talking here about 302 bound states that can live for weeks, essentially. So dipole transitions between them are forbidden. We only observe quadrupole transitions. And this kind of rare combination of theoretical tractability and experimental stability makes it a perfect benchmark system for testing molecular quantum electrodynamics and putting constraints on beyond standard model interactions. These are slightly different beyond standard model interactions that you've been discussing so far. I'm talking here about some models of fifth force, for instance, or higher dimensions that could be found at some point in the vibrational spectroscopy. Hydrogen could also, in near future, extend the family of simple species that allow you to determine fundamental constants. So in this context, that would be the proton to electron mass ratio. But in order to do that, both theory and experiment needs to reach this barrier. What I'm actually showing here is the historical progress in both theoretical and experimental studies of molecular hydrogen. And we have marked here in blue the experimental data points that were obtained using optical frequency comps. You can see how it revolutionized the field and actually gave us access to previously undetermined QED corrections. And interestingly, the fundamental limit on testing quantum theory with hydrogen, which you can deduce from the ratio of the natural line width of these quadrupole transitions to typical transition frequencies in the infrared, lies well below the 20th significant digit. So that's below the accuracy of atomic clocks. And of course, we are far away from there. We are currently 14 orders of magnitude away. So there's plenty of room to explore. And of course, hydrogen spectroscopy is quite challenging because I mentioned this exceptional stability, but this also makes it very challenging to detect these quadrupole transitions. We need quite sophisticated spectroscopic techniques, for instance, especially involving optical cavities. So we put molecules in cavities, and we have 2 highly reflective mirrors that essentially increase the effective absorption path length. So to give you some numbers, a couple of years back, we were very proud to hold the record for the best measurement in molecular deuterium, which probed these QED corrections to for the 4th significant digit. And with this ridiculously high finesse optical cavity, for the cavity which has 70 centimeters length, we had the effective absorption path length of 150 kilometers. So what I find particularly amazing with this result is that this accuracy was obtained at room temperature. So the other thing that you need to know about hydrogen is that the shapes of the molecular resonances are heavily perturbed by many things. I mostly study collisions in this context, but the thing that perhaps resonates with you the most is the fact that being the lightest molecule, it exhibits a huge Doppler broadening. At room temperature, we're talking about 1.5 gigahertz Doppler widths. So an obvious solution is to bring down the whole setup to cryogenic conditions, but it's of course easier said than done. Nevertheless, we are very proud to achieve our cryogenic high finesse cavity. And quite importantly here, compared to other hydrogenic experimental groups, we are cooling not only the gas sample, but the entire cavity, including the mirrors, the piezoelectric actuator. And we really paid a lot of effort to thermally shield it from the environment and to dump all the vibrations, both external and from the cryocooler and vacuum pump. So this is how the setup actually looks in real life. This is the cavity is inside. There are mirrors on the both sides of this tube. This is how it looks when you open it. And since we're interested in studying hydrogen spectroscopy, we would like to study the strongest transitions there are in hydrogen. And this is the fundamental vibrational band in molecular hydrogen, which is located at 2.2 microns. So of course, we also had to pay some attention and develop the laser system to get to this 2.2 micron band, but I won't get into details here. Nevertheless, after a few years of huge efforts, we have achieved our first cryogenic spectra of molecular hydrogen. So what I find here pretty amazing is how you go down with temperature from 7.8 Kelvin to 4.9, and somehow the absorption coefficient drops by 4 orders of magnitude. This is because there's a drastic relation between pressure and temperature in this cryogenic regime. We are working in the saturated vapor pressure regime, maybe not that far, but below the triple point of molecular hydrogen. So in terms of, and to our knowledge, this is the coldest H2 spectra that were taken in thermal equilibrium so far. In terms of testing QED, this is the theoretical prediction provided by Professor Pachucki, who's based in Warsaw here. And you can see that these QED contributions, they already show up at the 7th significant digit. Right now, we are an order of magnitude more accurate than theory. Quite importantly, we improved the previous best measurement by 3 orders of magnitude. Now, just to show you how we benefit from cooling down the sample, because I was talking about this Doppler broadening, this is the simulation of the same line at room temperature, which you can see it's very broad and not very intense. Just by cooling down the sample to 7 Kelvin, where we made the actual measurement of the line position, we gain a factor of 6 in terms of line narrowing, which is translated to the factor of 6 in terms of peak absorption. But then we additionally benefit from the fact that the entire Boltzmann population collapses to the ground or vibrational state, which essentially leads to this 50-fold increase in the peak absorption. So in the end, just by cooling the sample, you gain a factor of 300 roughly. And this is the most accurate measurement that was achieved with Doppler-limited techniques in hydrogen, not only homonuclear, but also heteronuclear isotopologues. And I will briefly say about some other applications of this cryogenic setup, because it's not that we only focus on QED tests. Turns out that we have built a very expensive thermometer. You can see here that you can relate Doppler width of your observed transition to the temperature. Actually, if you take a look at this formula, you will see that you have some fundamental constants here. You have some constants that you can determine experimentally, but their accuracy is far better than the accuracy of the Doppler width that we determined from temperature. So actually, we can determine temperature without any calibration to an external device, and this is how it compares with respect to some reference diode sensor, which is pretty good. So quite similar thing you can do with the amount of substance per unit volume, which you can relate to the line area. And here actually we are 2 orders of magnitude better than our reference. And if you combine the two, you get access to pressure using all optical methods. And you can actually probe the phase diagram of H2 below the triple point using only optical methods. So in the future, we believe it would be possible to determine also the H2 triple point, which is another interesting thing to look for, especially for chemists. But now going back to test of QED, this is where we are at right now, the 10 to the minus 10 relative accuracy level. Right now, we are working on implementing the saturated absorption spectroscopy, which we hope can get us an order of magnitude down. But we believe that in order to go further, it's necessary to trap a cold H2 sample, which is of course a crazy thing to say in public, because H2 has no electric dipole moment. It has a very weak nuclear magnetic moment. It has no cycling transitions, okay, unless you have a 100 nanometer laser and 5 more 100 nanometer lasers for repumping, because this is really an awful situation. But jokes aside, hydrogen has a relatively high vapor pressure in this cryogenic regime, which we aim to use to our advantage. So we want to develop a pretty deep optical dipole trap for molecular hydrogen, quite similar to what is being developed at Berkeley and Holger Miller's group, although their trap is even deeper. So we will start from our cryogenic source of H2, which is going to be kept at 4 Kelvin. And of course, there's a gap between 4 Kelvin and these hundreds of millikelvins there, but we plan to catch the coldest fractions of molecular hydrogen and benefiting from the fact that we start from simply a very large number of molecules in the first place. So again, there are many challenges that we need to overcome here, but because of the time, I won't get into details. I'll just show you how the setup looks like because it's being assembled this week in our group. This is the vacuum chamber where the whole thing will take place, and this is the PhD student for scale. Now inside of this vacuum chamber, you'll find the copper thermal shields that will be kept actually at 40 Kelvin. They will shield our setup from the room temperature blackbody radiation. And inside this, you will find the H2 reservoir. You will probably not see it, but there is a tiny orifice here. So we are not actually planning to form a molecular beam of H2, but rather like populate the trapping zone in an in situ manner. So we have the effusive source of H2 actually. And then like 1 millimeter away, we plan to launch our high power optical dipole trap and then ionize the H2 sample with the UV laser using a 2+1 Rampage scheme. And these electrostatic lenses will guide the ions so that we can detect them. So with this, we hope that we will be able to beat another 2 orders of magnitude. And there are, of course, some other challenges. Because of course you can ask me, okay, so you can have a dipole trap, but what about Stark shifts? So actually, yes, they will be enormous in molecular hydrogen, but luckily for us, we found magic wavelengths. They are quite atypical. They are not something that you would expect because classical magic wavelengths that involved excited electronic states, they lie in this extreme UV that I was mentioning earlier. We found magic wavelengths that are based on these narrow quadruple resonances in the infrared. So it turns out that in principle, you can find quite a lot of them close to these narrow quadruple resonances. And also we played with some other concepts, like simultaneously we are developing a magnetic trap for ortho H2 species. So it has a tiny nuclear spin, but in order to get, so we won't get that deep trap in this context, it will be probably closer to 1 millikelvin. But in order to get there, you need pretty strong magnetic fields. And we also considered some really interesting ideas to sympathetically cool H2 with lithium. This is the calculation we've done in collaboration with Timur Cherbul, where we have explicitly taken into account hyperfine and field degrees of freedom. So with this, I'd like to conclude. This is our group. Thank you very much for your attention.
Thanks a lot for this very nice talk. Are there questions?
So this is very nice setup, and I think chemists and especially theoretical chemical physicists should be really grateful. So, because you didn't mention, but would you be able to, let's say, study some chemical reactions with hydrogen which are easily simulatable at the best level of accuracy available?
And in principle, I think that it could be done. Yes, we like so far we only focused on non-reactive stuff. Like we also consider collisions in these conditions, but not in a manner that is known from beam experiments. We can actually probe collisions by looking at the widths and shifts of molecular resonances. So for instance, if my calculations are correct, then the H2H2 collisions in this regime are dominated by the single shape resonance. But in principle, yes, I think it could also involve some reactive collisions too. Yeah.
Thank you.
Guess maybe this is a redundant question based on what you just said, but do you see pressure broadening in this experiment?
That's a great question. Actually, I didn't get into details because of a time constraint, but also this is actually maybe it's gonna be seen from the So this is how the pressure drastically changes with temperature, right? So with our determination of the transition frequency, we were here. So you can see that the pressure is quite low. But indeed, so what we fitted to the experimental data is quite a sophisticated line shape model, which incorporates all these line shape effects. So not only pressure broadening, also pressure shifts. There's also Dicke narrowing that you can detect in molecular hydrogen. And actually, this is where my contribution was the most significant, because in order to reduce the systematic errors in fitting, you can fix these collisional parameters to ab initio values, and that's what I've done in this this context. So yes, we do see collisions. In fact, yeah.
Cool. Then let's thank our speaker again.
Thank you.